we neglected to discuss about what if we have some continuous homeomorphism between two Femboy spaces, right, or Bussy spaces. So consider this as another footnote, aside the one about the other four types of Femboy donuts. So, right, so, okay, we have one Bussy space B. Oh, sorry. We have one Bussy space B. B1. And then we have some another Bussy space 2. Bussy space. So, okay, so first we're going to discuss about homeomorphisms between two Bussy spaces. And then perhaps we're going to discuss about homeomorphism between two Femboy spaces. But when we talk about homeomorphisms between two Bussy spaces, we need to consider two types of morphisms. So the first is, of course, the homeomorphism, the one between two topological spaces. If we consider B1 and B2 to be topological spaces, our map between them, or morphism between them, is a homeomorphism. But if we consider that B1 and B2 are vector spaces, right? Because as I discussed in the lecture, these guys can either be a topological space or a vector space. Well, if it's a vector space, we need to consider a linear transform that sort of switches all vectors from this vector space to that vector space. So we need to consider that. And also for Femboy spaces, so say F1 and some F2. Consider these as topological spaces or vector spaces, and then we have some continuous function between them. So for here, let's say that psi that maps B1 to B2, and for here, this is some linear transform L, or switching positions that switches or that changes all vectors here and then turns it into the vectors here. Okay, so under L, the image of a small f under F1, so the image under L of a small f inside F1 is equal to some, so I'll call I, so it could be any one here, is equal to some Fj, Ij, inside F2. Okay, and so for this one here, this homeomorphism, the image of B1 or some f inside B1, or rather small b inside of B1, under psi of some small b of B1, so some open Bussy set, because this is a Bussy space after all, or topological space, is some open set B, this is Bi, Bj inside B2. Or if we want more compact notation here, I'll say that the L of Fi is Fj. And for here, the psi of Bi is equal to Bj. So it's a shorthand notation for the image. But if we want to be more specific, right, if we have two continuous morphisms between two structures, it's best to specify what image we're taking here, right? Because what if we have some psi and then some combination, right? So, okay, psi1 and a psi2. Such that these guys are not the same, okay? That's why we sort of differentiated them. So, one is not equal to psi2. That maps some topological space A onto B and C. So notice, if we we have these two topological spaces, notice that if we take if we specify that psi 1 maps A onto B and psi 2 maps A onto C, it's still a function, okay? Because it's an onto map. We have inputs here and then multiple outputs there. Okay? So yeah. Yep. So it's still surjective. We're still able to map it. Okay? So this is still a function. It's a valid thing. It's a valid thing to consider. So yeah, let's consider this map here, or these two maps combined together, or made shorthand. Notice how the image of A under psi 1 and psi 2 are not the same. Or rather, let's say we have some A element, small a in A. So given some small a inside big A, the psi 1 of A is not the same as the psi 2 of A. Because notice how if we have some B inside B and then some C inside big C, notice that the psi of psi 1 of A is some B, and then the psi 2 of A is some C, and this B and C are not the same because they're from two separate topological spaces. So essentially these two are not the same, but note that if they do map A onto the same thing, let's say if I only have B here, then they're practically the same thing. Or we can have some inverse map, and that would be valid. So over here, if I rewrite this as some psi that maps A onto B, two vector spaces, so function, and then B on the left here is mapped onto A via psi to the minus 1. Yeah, this is called a bijective homeomorphism because we have some regular function over here. It's probably a 1-to-1, and then we have its inverse. And since it has its inverse, it's probably a bijection. Most likely a bijection, actually. Majority of bijective functions, or actually all of them, contain an inverse. So that property there holds. So just need to tell you guys that, okay, so given some switching of positions that's unique, that means every vector has two possible inputs, right? So it's something like a piecewise function. It can be defined by a piecewise function containing two matrices or something like that, two n by n matrices. I suppose we need to figure out though, we need to specify what the images are under the function or the morphism, because ambiguity may arise because we already defined it or said that, well, we have two inputs or two possible inputs for our given, two possible outputs for a given input, right? Like how the square root of a number, or taking the square of the square root, so okay, taking the square of a square root of A it gives us plus minus A. But in calculus, they usually just pick the absolute value of A. But in general, it's a plus minus A. So we're given two branches of a given function, right? Or a given output. It can either plus or it can be minus A. And that's something. And then now we're thinking, how about topological spaces, right? How about our given Bussy spaces or our given vector Bussy spaces? Same thing applies basically. If we have some switching position here, or some linear transform L that maps B1, so two vector Bussy spaces onto B2. Well, let's say that B1 and B2 are just sort of collections of intersections between two sets or multiple sets that are tangentially or directly related to the bussy. So B1 and B2. If we have some map on them, some linear transformation or switching positions, then I suppose you need to specify what it is. And so, I mean, you could just say generally, yeah, this is a map that maps them, but consider the fact that, or consider the situation wherein we have two linear maps, L1 and L2, or two switching positions that switches every vector in this bussy space to the other. We need to sort of specify what the images are under these linear transforms, because notice how we have two inputs now. So we have, let's say we have a third bussy space here that's constructed from this and this bussy space. So I'll say that B3, not that. B3 is constructed from the union or the intersection between B1 and B2. Not that, but B. Alright, so now we have to consider what the images are, or what the outputs of our function are, because we have two possible inputs for our spaces. And I suppose we can define this function as something like this, or it can be something like a piecewise function constructed from GL and R. Perhaps for the two-dimensional case, it would be some two matrices from the general linear group GL2R. So we grab some matrices from this general linear group and then put them in some piecewise function that allows us to get two outputs. So I'm gonna sort of maybe define that piecewise function that defines our L1 and L2 in one way. And so, right, so for some B1, I'll say, so let's say our L1, L2 is equal to this piecewise function. So let's assume that B1 is something like, let's say R2. Let's assume this bussy space is some R2. Assume B1 is equal to R2. And then B2 and B3 are just subsets of R2, or still R2. So B1 is, okay, let's say subset, not the entirety of R2, subset of R2. Let's assume some more. So we're going to assume that these three are part of R2. So because vector spaces are usually part of R2. So B2, B3, and B1 are part of R2. Then let's define now, since R2 is two-dimensional space, we want our matrix, or if we want some clean transform that doesn't take it out of the second dimension or doesn't squish it into the first dimension, we want to maintain the dimension here, and it's two dimensions, of course. And so we want to have 2 by 2 matrices so that our basis vectors stay in the second dimension. Because if we have some non-square matrix like let's say A, B, C, D, E, F, this 2 by 3 matrix, this means that our I hat and our J hat gets transported into the third dimension because we have a third component to their vector, or to describing their vector. So we want, as much as possible, when we're working with R2, what we want to do is define a matrix that just simply changes it around. It just changes the vectors inside it. It doesn't really make the vectors 3D or one-dimensional. It doesn't squash them into a line, or it doesn't bring them out into the third dimension. That's if we want to not have a headache. But I mean, you guys can still try to do that. You guys can definitely construct a piecewise function that brings B1 onto a subset of R3. So if you want to define some square matrix or non-square matrices that are greater than rank 2, then it's probably going to be something like, okay, so let's say that this is some L psi. It would map B1 onto, well, same thing, B2, B3, but this time B2 and B3 are going to be subsets So with B2, B3 subsets of R3. But then B1 is a subset of R2. So what we're doing with this linear transform is bringing all vectors out of the second dimension, just a flat plane, onto 3 dimensions. So now we have 3 spatial dimensions. So our L psi would be something like, I suppose, A, B, C, D, E, F. Something like that. Or if you guys want, specify your K component, so we make it square, 0, 0, 1. So since we didn't specify the K component, or our 3-dimensional basis vector, or our 3rd dimension basis vector, then I suppose you can just write it as 0, 0, 1, or you can just say it like that. But note that once you apply this matrix, you would not be able to determine the determinant of this matrix. So if we have some shape that's changed by this matrix, you wouldn't know what it's scaled by, because only square matrices are matrices where we can find the determinant. If the matrix is non-square, we cannot find the determinant of it. So just quick note there, or quick warning, if you're working with non-square matrices. So going back to square matrices, or GL through R, that's actually another reason why general linear groups are only composed of square matrices. In fact, this general linear group is the group of all invertible invertible square matrices that have determinant 1. So an example with that would, I believe, be just the identity matrix. So 1, 0, 0, 1, that's a determinant of 1, and it's part of the general linear group, or factors of it. 2, 2, 0, 0, 2, something like that. That's also part of the general linear group, I believe, or actually no, I don't believe it is, because it's not of determinant 1, but you guys get the point. They have determinant 1 basically. Okay, so going back to our piecewise function, we want to define it as something like this. So if we assume that L1 and L2 are part of the GL2R group, or the general linear group of rank 2, then we define them as A, B, C, D, and then E, F, G, H. And then just for sum. So for sum, B in B1. And then for sum, B in B1. So that's our piecewise function for at least this general linear group. Or at least for these 2 morphisms. So L1 is this one here, this A, B, C, D, and L2 is this E, F, G, H. And to make sure that they're not the same, we made it such that the entries of these matrices, of these 2 by 2 matrices, are not the same. So that's why we use A, B, C, D, and E, F, G, H, so to make sure that they're practically not the same, and that their images are totally different. Okay, so that's one way of showing that your images are not the same, by basically saying, oh well, the thing is, if we scale them both by some factor and they stay the same, or they have the same result, then they practically are the same. But notice that if we apply these two on a vector, let's say xy, we would get a different result. So I'll show that here. So this is just basic linear algebra. This is just basic vector to matrix multiplication. So here. So now that we've defined our L1, L2, or our morphisms between our given Bussy spaces, or well, vector spaces, or topological, actually vector spaces, because yeah. Now we specify it. We want to show that L1 is not equal to L2. Okay, to show that L1 is not equal to L2, okay, we know that L1 is A, B, C, D over here, and L2 is E, F, G, H. To show that they're not the same, we just need to show, or just need to prove that when we apply them both on the same vector, we wouldn't get the same result. So let V equals some vector. I'll use a column vector in B1. So it must hold in order for B1 to be equal to B2. B1 applied on B must be equal to B2 applied on B. Okay. So we're gonna prove it via, or we're gonna show it via contradiction. So yeah, I'm just gonna erase this part now, and then I'll put it up top so that we can do our calculation. It's very simple actually. The proof for this, or to complete or to solve this, or to show it, it's very trivial actually. I'll define it here. L1, A, B, C, D, and then L2, E, F, G, H. And you guys already know that we're getting different results here. So X, Y. So, okay, we're gonna attempt to show that they're the same. Okay, so AX plus BY. So we're gonna turn it into a new vector. We get a new vector output. CX plus DY. And then now just do the same thing here. EX plus EY, or FX, no, EX plus FY, and then HX plus HY. And as you can see, they're not the same thing. So therefore, they're not the same matrix. So therefore, thus, L1 is not equal to L2. End proof. We also draw the box so that to signify that we ended the proof. So that's basically it actually. You can also show this for other things like scalars. So this not only works for vectors, but you can also show that if we have some scalar, say x, y, two scalars actually, or just one scalar x, and then we want to, if we apply that scalar on both of these matrices, if they are the same, it must be that they're scaled to the same product, or they end up in the same product. But you may notice that that may not be the case, because we literally have two different matrices here. So this just shows that given some vector, we're given two different outputs for that vector. Okay? And if the output of these two vectors are the same, then they're practically just the same, and they just merge into one, and you can save the pain, or just avoid the pain of trying to write a piecewise function for it. Okay? So that's for the vector space. How about for topological spaces? How about for our Femboy donuts, right? What if we want to define some homeomorphism or continuous morphing or function between one Femboy donut and another? So we say we have some FT1, FT2, say, and then we have another FT2 that's some morph of it. Like say a Femboy mug. Mug is basically the same. We can define the atlas the same way, but there is some continuous morphism between a donut and a mug. That's why us topologists think that they're practically the same thing. So for that one, it's also quite bijective too, because we can, given a mug, we can morph it back into a donut. So if I have my FT2 here, FT2, or my Femboy donut, and then I map it onto another FT2 here, that's let's say sub 2, to say that it's another one, it's different. And then we have the morphism here, which I'll call psi. Now notice how if there is some inverse map between these two, they are what we call isomorphic. I already discussed this actually, but I'm just doing some sort of recap or we're expounding upon the Femboy donuts. So, right, so FT2 and FT2 sub 2. These guys are the same. We can say these guys are the same, topologically speaking, not really physically speaking, but topologically speaking, because they're practically the same. We can just, if we imagine them both to be made of some pliable material like, say, putty or Play-Doh, we can just sort of stretch out the inside of the mug and then just shape it into a donut. And then that's what makes them practically the same thing, well, topologically speaking. Because when we study topology, we're talking about invariance over multiple shapes. So given like a ball or say a solid cube, when we try to study topology or in the vein of studying those shapes, we want to know the various things that don't change when we try to morph them. So when we try to squish the cube, or if we try to squish the circle or sphere, say, with topology we want to know what doesn't change. And generally what doesn't change is the genus. One thing that doesn't change about these two things are the genus. So if we have our Femboy donut over here, and then our mug here, so Femboy mug, I suppose. I suck at drawing these things, but bear with me. Okay, so we have our mug and our Femboy donut. These two are practically the same, because we can just bring the inside out and then just morph it into a donut. And then likewise for a donut, we just need to like squish it, like do this, and then just push it inside to get some mug. So there's some continuous function between these two. And so thus they are sort of homeomorphic to each other. And since they are homeomorphic to each other, they have some isomorphism. And notice that if we have some measure here, like say the surface area of this thing, or the total surface area, and the total surface area of this thing, we have something called an isotopy. And when we call isotopy, or we say isotopy, an isotopy is some continuous deformation of a measure over some object. So think of it like a morphism between morphisms. We know that a measure of an object, a measure which we call, say, D, like distance, is something that maps a set A onto R. So it returns a value as a function of a given shape or set A, such that we're given some real number. Let's say distance. On a line, if we take its measure, we would be given some real number that dictates how long the line is. Likewise for a shape, if we want to specify some measure on it, right, say have some D that maps it onto R, you can say that it gives us a real number that describes the surface area of the object. Likewise, if we have some measure over our Femboy donut and our Femboy mug, if they are practically the same thing, topologically speaking, we can say that their measures, which I will call D1 and D2, are isotopic. So D1 and D2 are isotopic, or contain an active isotopy. And that's one of the most interesting things about topology, actually. When we're trying to determine the isotopy class of two shapes. So we say how many times can we deform them into the same shape, right? So we can deform this into just a regular donut, and then we can deform that into the same donut. That's another way of saying that we have some isotopy or some active isotopy between the two measures of these things. So, and also saying, since the two measures are isotopic, we just say that the shapes themselves are isotopic. The same thing when we study knot theory, or when we talk about knots and stuff like that. We also want to determine whether two knots are the same. And one way of determining if two knots are the same is if they contain some active isotopy. So when we try to integrate knot theory into our course, there's some specific anisotropic reason why I tried to study knot theory, but that's not important right now. When we try to apply knot theory in our course, it will definitely be useful for us to study about isotopy and having, same measure or continuous deformation between measures. So, okay. So I'm gonna formalize the definition of isotopy by saying this. Given two measures, or metrics, and the terms are usually interchangeable, which I will call D1 and D2. If there exists, if there exists some psi that maps D1 to D2, and there exists some psi to the minus 1 that maps D2 onto D1, or rather the image, let's say the image. Since we have this is a metric after all, we want to say that it maps the images, not really the metrics themselves. So the image of D1, or rather the image of our given set or metric defined over these guys. So let's say that D1 defines some metric over a set A, and D2 defines some metric over a set B. So the image of A under, D1, obviously, we know that. So image of A is D1, is the image under D1, we know that. So it maps the image of A onto, or it maps every image of A onto some subset of B. B subset of B. And then likewise, some image of B, small a, because it's an elemental set, small a, in A, and then small b in B, onto some A, subset of B, A. So if this case holds, or this property holds, D2 and D1 has an active isotopy. And A and B, both either topological spaces, maybe surfaces, manifolds, or sets in general, that can be mapped, of course, onto R. And A and B are isotopic. So isotopy is a very important thing in topology, actually, and in knot theory. And when two shapes have an isotopy or are isotopic, they are practically the same thing. We can say that A and B are equal. And so that's actually another way of trying to construct the Banach-Tarski paradox by showing that two shapes that are fundamentally different have the same isotopy, or are isotopic to each other. And this is a very important method of finding out if two knots are the same, as I said a while ago. That's why it's very important in knot theory. And it's a formal definition of showing, or of defining, or showing, or explaining, or rather just saying that two knots are the same. Like, let's say that, for example, let's say the trefoil. If I can draw it correctly here. Yeah, let's say we have the trefoil. Now, if we have another knot, let's say there's another one here that's sort of like the trefoil. It still has 3 crossings. I think this is it. 1, 2, 3. So this knot here. Well, they obviously look different, right? But notice that they have 3 crossings here. That's one measure of it that maps sort of what we know about this onto R. So it maps this knot onto R, saying that, well, 3 is a real number. It's saying it has three crossings. And then here, we say it has 3 crossings. Since it has 3 crossings, then it's only 3 colorable. So we can only color each arc with 3 colors. So 1, 2, 3. So likewise here, also color it with 3 colors. 1, 2, 3. And because 3 is some invariant measure towards these two guys, we're saying that the measures, which is just 3 and 3, are isotopic. Or let's say D that maps us onto R. And the image is just 3, basically. So D here and D here are the same thing. They map these guys onto the same number. And because that morphism, or that psi over here, is practically the same thing. It maps the image of A onto this one here, and then likewise this onto here, or the image of this onto here. Then we're saying that D here and D here, or the measures, are isotopic, or have some active isotopy. And so therefore, these two knots are the same. But I must note that determining isotopic classes of two knots is not the most definitive way of determining if they're the same. But this is just an example, basic example of why isotopy is very important. Because as we can see, they are practically the same, even though they look very different. Topological speaking, or speaking with respect to their invariance, they are the same. So one invariant, of course, is our crossing number. It never, given a knot, crossing number never changes. So yeah, crossing number here is 3, no matter how many times we try to pull apart or whatever we try to do, except without cutting it, it would stay the same. So that's it for this footnote. I know it's not quite, it's a bit long, 7 minutes. It's just a footnote after all, but I suppose that's what I need to discuss about these things, isotopy. So in general, so in general, this footnote is summarized into these facts. So, given some switching of positions, so we have a bunch of femboys inside a femboy space. 2 linear transforms or switching positions are not the same. So this is the first fact that summarizes our lecture, or our footnote, are not the same if and only if applying them on the vector yields different results. The second one is just the one that I just said just now. 2 sets or structures are isotopic if there is an active isotopy between the measures of the sets or metrics. So that summarizes our lecture, right? And so, yep. Isotopy and, non-similarness of switching positions, or 2 linear transformations. So yeah. So under this one here, I just need to add that the eigenpositions under this and the eigenpositions under this are different also. But maybe there are some matrices out there, 2 transforms, linear transforms, that are probably part of GL2 or GL2R or GL3R. There are probably some matrices out there that have the same eigenposition. We just need to show that they're the same, or there's a chance. But that sort of undermines our definition of 2 of these guys not being the same, because when we apply them on a vector, it's not the same. But okay, given the case that they do have the same eigenposition, that means if we apply apply this on that eigenposition, we would get some scaled eigenposition, right? But at the same time, I can still undermine that argument because I can say that, well, eigenposition is just something that we find out of it. It's just another vector we obtain from it. Apply this transform. And if we apply these guys on the eigenposition again, it might be that the eigenpositions don't get scaled at all. Or maybe they just, I suppose they still get scaled and they still get scaled and so they're still practically the same. But there's a chance that, there's a high chance, or maybe just 100% chance that the two eigenpositions are gonna turn up different when we apply it again on the eigenposition. So that's it for this footnote.